Thank you for coming back. So as was announced yesterday, I will give you some ideas of the proof of Landis conjecture in dimension 2. We suppose that we have a function on the whole complex plane that solves this equation. The only thing that we assume about the potential is that it's in L infinity. We can always renormalize, so we will assume that the norm is bounded by 1. And we want to show that if the function decays too fast, then the function is 0. So the statement suppose that for some large constant, u of x is bounded by e to minus this constant x times log x for large enough x, and c is larger than c0, then function is a 0 function. This is the statement that we're trying to prove, and there will be 3 steps that I will try to describe. I'll give you some of the details of those. Yeah. Important thing that I did not mention is that the function and the potential are real valued. We're going to use this a lot. That function takes only real values. It's not a complex valued function. And it's, I think, mostly used in the first step, where we're going to do the following. We will fix some large R, and we'll always look at the behavior of our function in a large disk. And let F0 be the points in the disk where the function is equal to 0. As I mentioned yesterday, if the function is positive or negative, then we know that it does not decay faster than exponential by Harnack principle. We're not going to use it explicitly, but we expect that if we have a function decaying like that, there are some 0 sets. You can also have a closed lines. There is no maximal principle for this equation, but you can have something like that. This is the 0 set there. And we know that 0 set is not very bad. For a very good 0 set, but you can add something like that. This was almost good, but this is not so good. Let's do it like that. When they cross the lines, they cross in equal angles. Because locally, if you zoom in, you don't see the potential, you have a harmonic function. So we know that locally the structure is nice, but it's not important for us here. And the first step is to create some holes in our domain, because our aim will be to find another solution to our equation in some subdomain of this large ball. And we want this solution to be small perturbation of 1. So we want a function that is almost 1. Why I write c epsilon squared is not so important here, but think one function phi between 1/2 and 2 that solve the same equation. I cannot do it in the whole ball, but I can try to find a subdomain of the ball where I can do it. And the thing that should be related to being able to solve this equation is the first Dirichlet eigenvalue of the domain, that is infimum over functions that are equal to 0 on the boundary of the Dirichlet norm. Divided by the L2 norm. So we're trying to make sure that the domain that we're going to construct has very large first Dirichlet eigenvalue. If the first Dirichlet eigenvalue of the unit ball is constant, that depends on the, I don't have a dimension, I have dimension 2, but I'm not going to give you the constant, then the first Dirichlet eigenvalue of the ball of radius r scales like r squared. For the small balls, it's very large. For large balls, it's very small. And you can also think about this constant as a constant in the Poincare inequality for the domain. So we do the following thing. We have our first omega 0, that is ball minus the 0 set. And we will fix some positive epsilon. Think epsilon is small. And create balls of radius epsilon in each connected component of this domain. So this is a finite union of connected components. In each of them, I want to take a 100 epsilon dense set. So xj is a discrete subset such that if I take balls of radius 100 epsilon centered at this point, they will cover everything. And the distance between two different points in this set is bounded by 10 epsilon. I'm lying to you because you can go to the end of the proof and see the constants. The constants are much larger here. You have like 10,000 here, 1,000, something like that. But you can, from the end of the proof, you will see that you can do these constants carefully, but there are some constants for which you take the set like that. One more important thing that I want is that the distance from each xm to the boundary of this domain is, oh, sorry, yeah, sure, they're well separated. For any 2 points, the distance is large enough. And this is also true here. So this was my connected component, and I am taking a balls, small balls of radius epsilon here. I don't want to come close to the boundary, and they are well distributed there. Maybe you just can take a lattice and take all the points in this lattice that are in this part of the domain. So F1 will be the union of all these j's, and for each j we take a union for points in this discrete set of balls of radius epsilon. So this small balls here. I claim that for this domain, the first Dirichlet eigenvalue is large. So now my domain omega is the wall radius r minus the initial zero set minus f1. So I need to prove a Poincare inequality with a large constant. So I want to show that for any function in this set, the integral of the gradient of f squared is like that. And roughly speaking, you're just using one-dimensional Poincare inequalities and saying that this function is equal to 0 on the boundary of this and all the balls. So I want to bound the gradient here, the integral of the gradient. This is a small interval of length comparable to epsilon. I'm lying to you because if I will just take a point there so that you cannot inscribe a circle of radius larger than 100 epsilon into the domain, this will not be true. But since I have not a points, but I have a holes of size around epsilon, you can show that this is the case. So C is a large constant, I don't know. C is some constant. This constant C will depend on this 10 and 100 that I choose here. Yeah. So we need to know that you can look at this integral and do integrals like that, but this is a bad way to integrate over a space using integrals over the lines. But it's better only around this point. So if you give me some room and say that there is a zero set that is a circle of radius epsilon, this is still true. And it's not a difficult exercise. The next claim is that this inequality allows you to solve the problem so I'm trying to solve the Poisson equation, or in other ways, I'm trying to find a function in the domain that is 0 on the boundary, and I can do it with a control of the solution. And I need two versions of the control. I want to know that the L infinity norm of this solution is bounded by the 1 over this guy times the infinity norm of V. And its norm in W01. 2 is bounded by some constant, depending on epsilon times the L2 norm of V. This norm cannot, it's not a nice norm to write this inequality because it doesn't scale in the right way. You have both first derivative here and the function, but if you fix a domain, there is some inequality like that. And we hope that there is a textbook where you can find those inequalities. but we didn't manage to find the textbook, so we had to write it carefully, but there is nothing very complicated in there. Now, if you believe in this claim, you can construct my function phi that I like in the following way. So you first solve the equation like that with the control of the function. It's small infinity norm, it's some bounded norm in W0, 1, 2. And then you do iterations and solve the equation like that. And then you can check that the series converges, and your function is just 1 plus sum from 0 to infinity, phi k. You apply the Laplacian, one will disappear, you have Laplacians of those, and it will give you exactly minus v times the function itself. So Laplacian phi plus v phi is equal to 0. But remember, what is my domain? My domain is the ball minus all this. Oh, this is. So, what is my domain? My domain is this one. So it's one connected component minus these balls, and I have a function in here. So this was the domain. Yeah, I will do it separately for each domain, and you'll see why. So I will do it not for the whole omega, but for each omega j minus the corresponding points. And I will have a function psi j here that solves this equation in this domain, j's connected component minus these balls. But the function phi j is equal to 1 on the whole boundary of my domain. And it's easy to see that it is like that, like from this inequality, saying how we constructed the solution. It satisfies this inequalities, and it is on the boundary of omega j minus these balls is equal to 1. Then the next claim, that is one more technical thing to check, is that when you define a function v that is the ratio of your initial solution and this phi, just the algebra will tell you that if you take the divergence of phi squared gradient v, this is the divergence of phi gradient u minus u gradient phi. So it solves this is 0. This is the Laplacian of each function is v times the function. But what I'm claiming is not the algebraic part, but if I defined v such that v is equal to this in my omega j minus the union of the balls, Then this function v that is defined separately in each part solves the right equation in the whole domain omega. So I have the union of these domains. My balls are getting smaller and smaller. It's only on the picture, and they shouldn't go close to the boundary. So what we're saying that if you go between those two domains, the function u is 0. So your function has a good value there, it's 0 function, and you need to carefully check that this is true in the weak sense by doing the integration over each part and see that there is no problems created on the boundary because the function u was 0 there. So this was the first step. And as a result of this step, we have a solution to divergence form second-order elliptic PD, which we like better than Schrödinger for some reason. And the price is this holes that we created in our ball. Yeah, now I will say that I can go across those, so this is actually in BR minus the balls that we created. We can extend this as a solution across the 0 lines of the function. Step 2 is why we like divergence equation. So what does it mean that divergence of phi squared gradient v is equal to 0? Suppose I'm thinking locally now. I have two functions, the x derivative of 1 plus the y derivative of the second is equal to 0. Then I can find a function. So this is a, yeah, I'll write that down, but we know that each closed form is exact in a ball. So I can find function b tilde, at least locally, such that the derivative in x of this one is b tilde y, and phi squared, the derivative of y, is minus v tilde x. I'm trying to check that I'm writing the Cauchy-Riemann system if phi is equal to 1. So I want to say that v plus I v tilde satisfies some equation. If phi was equal to 1, this is just an analytic function, holomorphic function. If not, it turns out that you can compute d bar of this one, and it will be equal to 1 minus phi squared, 1 plus phi squared, vx plus y, vx minus times the d. So the derivative in z bar of this function is a multiple of the derivative in z of this function. And moreover, if you look at this coefficient, it's less than 1. We say that this is equal to 1 if you, on the point where the gradient of v is equal to 0. So we have this coefficient mu. moreover, it's not only less than 1. I chose my function very close to 1, so this coefficient will be bounded by constant times epsilon squared. And now I will forget about the way I got to this coefficient, because I don't want to do things locally. I will just say, let us look at this coefficient. And we will extend phi to be 1 on the complement of the ball of radius r. So we'll have a function that is bounded by constant times epsilon squared, and it has a compact support. I'll need a few things from series of quasi-conformal maps. And the first is that there is a map from the complex plane to the complex plane. That is a homeomorphism that solves the corresponding Beltrami equation. To construct it, you consider a solution that behaves nicely at the infinity, and then you prove that actually it's a homeomorphism. So we are looking at this solution to this equation. There are many, but there is one with prescribed behavior at infinity that actually gives you homeomorphism of the whole complex plane. And phi is a k quasi-conformal map where k is bounded by 1 plus the bound that we had on mu. So we have a map phi that is from the complex plane to the complex plane, and it solves the equation like that. And I want to only look at it at our initial ball of radius r. So it maps this ball to some open domain. And then I want to transform it back to the ball. So now take a conformal map that sends this point back to 0. Then the composition still satisfies the same equation. When you compose a solution of the Beltrami equation to holomorphic function, you will have the same equation. And now I'm claiming that if we take a function h that is defined under unit ball, I want to go from this ball here. Then I want to go from here to the ball. And then I want to apply my function v function w, function v, yeah. Function v that I had before. So w, I don't use it, I just used it as a motivation to find my mu. I don't know what it is, it's defined locally, but I don't want to think about it. But I can look at what should be a real part of this w applied to this convolution, to this composition. And then there's an exercise to check that this is a harmonic function. It's how we think about it. It's this w and this guy solve the same Beltrami equation. We do the composition of those, then the composition is a harmonic function. It's harmonic function where? It's harmonic function in our B minus the balls that get into some strange perturbations. We'll never think about this function, we will always think about the composition of those two, because the composition of those two is also K quasi-conformal. Map, it's a convolution of a quasi-conformal and conformal one. And probably I should say 2 words about what quasi-conformal are. Conformal maps don't change the ratio, and the quasi-conformal maps don't change it too much. So if it's a homomorphism that is 1-to-1, and in addition, we want that if you look at distortion around point x0 on scale R, this is I wanted to write one over to be sure that it's, I'm not dividing by 0, but we were saying that there is a limit of those. And it's large enough, larger than 1 over k. So the distortion is bounded by k, the coefficient k. If you look at the image of the small ball around your point, the distances could change, but the ratio is bounded by k. You have an ellipse where everything is happening. The quasi-conformal maps are not Lipschitz. There is more distortion that happens to the distances. But the inequality that we're going to use is the following. If I have a quasi-conformal map F from the unit disk to unit disk, that keeps 0 in place, then the distortion is, or the difference between two values of f are bounded from above and below by a constant that is actually precise. It's 16. I don't need the value here, but this 16 will affect my 100 that I had before. Times z1 minus z2, 1 over k, and 1 over 16, z1 minus z2 to the power k. So it's not exactly Lipschitz, by Lipschitz, but there is some control on the change there. If you don't care about the constant here, and you know a bit about quasi-conformal maps, it's not so difficult to see it, and there is a very nice proof that uses as a parametric inequality to check that this function is Hölder continuous and this is the right thing. I don't think I have time to go there. So we have our new domain where the function is harmonic. And what is this domain? This will be my function f. It is also k quasi-conformal as the inverse of the quasi-conformal map. So h is harmonic in, maybe I want the inverse of this. So minus the image of the function f of the union of my balls. I want to know how balls of radius epsilon are changed when I do my quasi-conformal map. And this is when I am going to choose my epsilon. So I want this to be looking like a ball at this point of radius comparable to epsilon. It's not important for me that it's a ball. It's important that I can say that this thing is contained in something that is less than 10 that was 0, less than half of 10. I'll write 2, but this is a lie. I cannot do it like that, but I can have some constant. That is not pretended. This is some large constant times epsilon. So I want to know that when I do my quasi-conformal map, things of size epsilon don't change much. This was the Morris theorem for the unit ball. I don't work on a unit ball, I work on a ball of radius r. So this whole f is a still quasi-conformal map on the whole R. We constructed it everywhere because we had this coefficient mu everywhere. So the quasi-conformal map is everywhere, but the equation for our function is only here. So for our, this was f0, to say that it's not normalized as ours, but for our function f, we know the same thing but divided, normalized by r. So if you want things not to change much and you want your function to look like a Lipschitz one, if you care about size here, that is like epsilon over r. What k can you allow yourself? And it turns out that the k that you can allow yourself is like 1 plus small constant over log r. That everything that was comparable to between 1 over r and r will not change much when you do this. So remember, k was like 1 plus constant times epsilon squared, so we want epsilon to be like 1 over square root of log r. And then this is much larger than 1 over r. And as I said, everything between 1 over r and r does not change much. This. And if I take two points very close, I don't know what the images are. But if this distance is at least 1 over r, it is multiplied by a constant at most. And we care about the balls of this radius, so maybe. I'm not sure about 2 here. I mean, I also have this 16, so I think you need to do at least something larger than 16 to be there. So we know that our function is harmonic, and it's harmonic in this set. And we also said in the very beginning that our function did not change sign, the function that we constructed. The main thing that I said several times yesterday, but I probably forgot to tell you today, that the nice thing about the function here is that v is never 0 around each ball. Because balls were far from the 0 lines of our function, v is just function divided by phi. It's very similar to our function. So there is an area here where my function doesn't change sign. Once again, this 5 is very optimistic. I will need to take some larger constant here to be sure that when I go to h, it has the same property. That around each hole that I now making a times larger, I still have a place where the function had the same sign. So I will also need something like b of f g 5a epsilon should be in the image of a large constant epsilon here. And the reality is that I want all this annually to be where my function, my initial function, has a precise sign, plus or minus. Then I know that now I have some fixed domains where function h is non-zero. And we're finishing with the last step that I will do. Yeah, so now we have a large ball BR, a function with new centers that are of this size, and h is equal to 0, intersected with each like that. I want to rescale everything to the unit scale. This epsilon is of the size 1 over square root of log r. So when I will rescale, the picture that I have is that I have a ball of radius r tilde, that is r square root of log r. And our h tilde is a harmonic function in this ball to do a somewhere there minus union of balls of radius 1. And this is where the square root of absolute value of x comes in the final statement of the Landis Conjecture. It's how much we can allow ourselves for the epsilon. We cannot take the epsilon larger than this one, otherwise our quasi-control map changes things too badly. So the last step is to see that if you have a harmonic function that is harmonic in the whole R2, ER tilde minus union of these balls, then it should not be very small near the boundary. It is actually what we prove, but I don't want to do that. I will do the toy version of it. If the function is harmonic in the whole complex plane minus the union of those balls, and doesn't change sign in nearby, then H cannot decay faster than now without logs E2 minus large constant times absolute value of x. And this is a very important condition. I don't know how to relax it. One question that I know from Carlos Koenig is, suppose that you have a function like that so that it's just equal to 0 on the boundary of the ball, but there is no structure in these balls, no periodic structure. They're far enough, all of radius 1. Can you say that your function is not decaying fast? I don't know how to do it. Our condition is much better than just 0 condition on this thing. So our condition tells us that if you think about, you can enlarge your hole a little bit, but then here, in the middle of this one, you have a function that satisfies Harnack inequality. So all the values are comparable, and the gradient is bounded by the same quantity. So we have a very good control of what our function is doing near each hole. Maximum is comparable to minimum, and the gradient is right. So let's say it is in each domain like that, we know that our function h is comparable to some value on this domain, and the gradient of h is comparable to the same value because I'm on scale 1 now. And the last one thing that I want to show you is that this toy version is true, that there is no such function in the whole plane minus those holes. Suppose that such function exists, and we will look at if I have a harmonic function, the gradient of this function is an analytic function. If you think about the gradient as in the right way, right? So this should be an analytic function. With either plus or minus, I think minus, but say if my function is xy, it's like that. And I will look at this one times an exponential function. Suppose that I know that my initial function h, or h tilde, that is the same as h now, was decaying faster than exponential with this key, or at least like exponential, then this is a bounded function. When you have a bound on h, you have a bound on the gradient of h as well. Everywhere far enough from your balls you have it, but you have it on your balls as well, because in each ball the Harnack condition gives you this one. Bounded holomorphic function on the complex plane minus union of 3 times the balls. So we have maximal principle that tells us that there is some maximum of this function. I will look at the ball of radius 3 around this point. Yj was a bad notation, but I will take this point where the real part is largest and say that this point is Ej. So at this point, my function, this part is approximately mj, the gradient, and the exponential part is approximately, or exactly this one. This is a value, more or less, of my function f at Cj. It's a bounded function, so this sequence is a bounded sequence. Also, take this case slightly larger, so that it's decaying function. And then we know that there is a point where it takes a maximum. Then there is larger than any other of them. Now you look at this point, and you travel this way. There is a particular way because I choose my k to be a real number, so there is a particular way where my exponential is growing. And we are saying that we can control the gradient of our function h over here. So we're looking at the value of our u and z j minus u and z j plus t. Somewhere here, that is the integral from minus integral from 0 to t ux. And there are two things that could happen. Either you go far away and you don't see any other balls, so you can continue as long as you wish, or you start here and then you see another ball at some point. Here you have two values of your function u. One is approximately j0, another is approximately j for another j. And I claim that with this information, this is a simple exercise to show that this integral, in this case, when t goes to infinity, this is small one. I have an exponential decay here, and my initial condition is comparable to that one. And I'm saying I will never reach 0 if I choose my constant k large enough. And this more or less the same thing happens here. You don't have time to go from this value to this value along this line because you have it bound on the gradient of u. This is a nice exercise. I think I will spare time and not do it here because it's time to catch my train. So I'll stop here. Thank you. Yeah. Yeah.
But for instance, Kahneman estimates are stable enough to allow differential inequality. Is result true also for?
Yeah, but I mean, I think the main thing we're doing this quasi-conformal map, right? So you're saying that if no, I don't know what to do. I mean, the thing is, you can think about it, it's still about inequality because I don't know anything about my v, right? Everything I said is for the inequality Laplacian, u is bounded by u. But then I use this ratio to do the machinery, so yeah. Also, as I said, I think the Malin inequalities are very nice because they don't distinguish much between equations and inequalities, but they also don't distinguish between real valued and complex valued. And it's not clear how to tweak the Kerr-Lehmann to distinguish. Probably there is a way to think about it, but I don't know.